So today we're going to continue talking about the gross structure of our planet, and then hopefully this will segue by the end of the lecture today into a discussion in particular on the shape of the surface of the Earth, which turns out to be related to its overall structure. And finally, if we get a chance, we'll talk a little bit about some more detailed issues having to do with the shapes of the ocean basins themselves. And so hopefully we'll get a chance to come back to this picture, which is our planet. It's an equal area projection, so of course we live on a spherical planet. In order to make it a nice flat map that you can project onto a screen, you have to do something to it because it's hard to squish out a spherical shell into a flat piece of paper, and this is a particular mathematical transformation to do that where area is preserved, so the individual continents and oceans take up as much area on this map as they do, proportionally speaking, on the planet. The price you have to pay is that out here things get kind of curvy, but no big deal. We'll come back to this. Okay, so at the end of the lecture on Monday, we started talking about the overall structure of our planet. And so this is just a cutaway of the Earth. This is the blue planet picture taken by the Apollo spacecraft 40 years ago. And then it's cut away to show that the Earth has a dense metal core, iron and nickel metal. Underneath, a rocky mantle, and it's roughly color-coded here. And on top of that, there is a thin crust, which on this picture is so thin it's like 1 pixel wide, but it would be floating on the surface of the mantle, essentially. And this is a differentiation by chemical composition. Metal at the middle, magnesium silicates mostly in the mantle, and then aluminum silicates in the crust. And it's also differentiation by density. The most dense stuff has fallen to the bottom, to the center of the Earth. The metal is by far the most dense. Mantle is next most dense, something like 3.2, 3.3 times as dense as water. Then the crust is the least dense of them all, something like 2.7, 2.8 times as dense as water in the case of continental crust, maybe 3 times as dense as water in the case of oceanic crust, and that's floating on the outside. And then, of course, less dense things like the oceans themselves are effectively floating on top of that stuff, too. Okay, and just to remind you, I brought these on Monday, but in case you didn't get a chance to see them, we actually have examples from the Earth of continental crust, the least dense of the major rock types, and sort of the characteristic rock would be granite. There are, of course, many other kinds of rocks in the continental crust, but this is perhaps typical. Light-colored, in this case, fairly coarsely crystalline. Oceanic crust, which is a dark-colored volcanic rock. It's a little bit more dense. This is maybe 2.7 times as dense as water. This is maybe 3 times as dense as water. This forms the oceanic crust. And then finally, mantle rocks, which are occasionally brought up by volcanic eruptions. And there are actually some places on the seafloor where you can go and just scoop them off, where the mantle's actually been brought up to the surface by faults. And typically kind of a greenish rock. That green mostly comes from a mineral called olivine. So think olives, green. That's actually where the name of the mineral comes from. And that's got a lot of magnesium in it, which tends to make it more dense than the crustal rocks. Okay, so it's densest of them all and tends to be at the bottom. Unfortunately, I had to give back the iron meteorite, so I didn't bring that in today. But you'll actually get a chance to see an example of metal to play with by yourself to see if you can determine the difference in density between these types of rocks just by weighing them with your hands, which many of you will be surprised how good you are at doing that. And that'll be in your lab either next week or the week after. Okay, and then right at the end of lecture on Monday, I started talking about a different kind of layering in the Earth that comes from the interplay between this chemical layering from least dense at the surface to most dense in the center of the Earth, interplay between that and thermal structure of the planet. Our planet is hottest in the middle and coldest on the outside. Okay, because there's radioactive decay occurring in our planet that generates heat that has to get out and eventually radiate away to space. And in the process, of course, it works its way up to the surface down a temperature gradient until you get to the surface where it can escape to space, and that's going to be the coldest part of all. Okay, and rocks, like most other things, tend to become weaker as they get hotter. So rocks at the surface of the Earth are the most brittle, the most strong. Okay, they're like rocks. Okay, you couldn't take that rock and squeeze it into a Play-Doh mold and turn it into spaghetti or something. Okay, that would be very difficult to do. However, if you get rocks hot enough, even though they are still solid haven't melted yet, they become progressively weaker and eventually actually become able to flow on very long time scales, millions of years. Okay? And this is going to happen as you get deeper in the planet. So we have cold, very stiff rocks at the surface, and then as you get deeper and warmer, they become progressively more plastic. They start to flow. Okay? And we make a fundamental division that's going to be really important for understanding why the oceans have the shape they do between what we call the lithosphere, which is the topmost part of the Earth. That includes the crust, and the uppermost, coldest part of the mantle. And that's the part that's so cold it's basically brittle. Okay? It doesn't flow. It can crack. It can have earthquake faults on it. Okay? But it's not going to flow around. And then once you get deeper than roughly 100 kilometers, you get into a part of the mantle that's so hot it actually can flow on long time scales. And we call that the asthenosphere. Okay, so we have cold, strong stuff floating on top of, essentially, hot, more plastic stuff. It's all solid, okay, but the stuff on the bottom is hotter and therefore weaker. Okay? And so we're going to come back to this, but the basic idea here is we have this cold, stiff stuff that's essentially floating on top of a more plastic part of the hotter, deeper part of the mantle. Okay. And it turns out that there are actually more layers than that as you go down further. We're mostly going to focus on lithosphere and asthenosphere for this class. However, just for the sake of completeness, in addition to this uppermost strong, solid lithospheric layer, and the asthenosphere, which is right underneath it, which is weak, but still solid. It can flow, but it's still solid. If you picked it up, it would be a rock, okay, once it cooled off and you got cured for the burns. As you go farther down on the Earth's mantle, beneath, say 300 kilometers or so, okay, it's still getting hotter, but the pressure is getting so high that, and there are also mineralogical changes that occur because of that pressure, that it starts to get stronger again. Okay? It turns out that the temperature actually doesn't change very much from the top of the mantle to the bottom of the mantle compared to what you might think. And so pressure actually becomes more important and the mantle becomes gradually more, or not so much gradually, but eventually more solid. It can still flow, so I kind of left it in this weird pinkish color to indicate that really the whole mantle below the lithosphere can flow and circulate, okay, but not as easily as the uppermost few hundred kilometers. Then, of course, when you get into the outer core, that's liquid metal. Okay, and it's really runny. Okay, it's got something like the viscosity of water. Okay, so you could pour a glass of that stuff before the glass caught on fire. And then finally, in the inner core, we have solid metal again. And I'm not at least enough of an expert on the structure of the core to know how strong we would consider that as a solid material, but nonetheless, eventually you get to solid metal again. Okay, so we're really going to focus on these two. We're going to talk about the fact that the whole mantle can circulate a little bit. When we start talking about magnetism in the Earth, we'll mention in passing the fact that the outer core is liquid. So we have these three layers that are actually sufficiently plastic that they can flow underneath the uppermost layer of the Earth, which is stiff, solid, and really only deforms by fracture rather than by flow. Okay. So here's a common misconception, even for people who should know better. Some earth scientists actually run into this problem. And in fact, there are some really prominent earth scientists who really don't believe this is true, but I'm going to give you the consensus picture. This is a general education class, just bearing in mind that there are people who may disagree with what I'm about to tell you. And that is that the mantle really isn't melted. Sometimes you'll hear people talking about, underneath us, everything gets molten because it gets so hot. That's really not true in most places. If you were sitting here in California to drill a hole, most earth scientists would wager with you that you would have to go all the way down the mantle, essentially, before you started reaching significant quantities of molten rock. Okay? The rocky part of the Earth is basically solid as far as we know. Okay? There are a few places, a special few places in the Earth, where you do actually see molten rocks. Okay? And those are associated with volcanoes. Okay, duh. Volcanoes where liquid rock's coming out of the Earth. But in particular, the most dominant volcanism on the Earth takes place underneath the oceans at mid-ocean ridges, which we'll talk about later today and on Friday as well, and actually for another week or so. And this is an area we'll come back to where we're generating new oceanic crust. Oceanic crust, this stuff, okay, is a volcanic rock. So it's rock, at least the upper part of the crust is rock that's come out of a volcano on the seafloor. And the very uppermost part of the mantle there, we think, is actually flowing upwards towards the surface. And as it rises, its melting temperature drops. okay? And it eventually starts to melt a little bit, maybe 10, 20%, something like that, and that melt rises up and eventually erupts at volcanoes to make new oceanic crust, okay? But if you go down below roughly 100 kilometers in most places, even underneath the mid-ocean ridges, it's pretty much all solid. Okay, if you go to the side of the mid-ocean ridges, and almost in most places, it's solid. Underneath the continents, the mantle's pretty much solid. Okay, so vast majority of the Earth's mantle is thought to be solid. It's not generally molten. Okay, but it can flow. It's solid that can flow. So this turns out to be important, this property of hot rock, that even if it's solid, it can still flow, is really critical for understanding how plate tectonics works. It's really critical for understanding why the oceans have the shape they do. And in particular, one active area of research for a long time and continuing for Earth scientists is understanding how the Earth's mantle flows in response to this process of removing heat from the interior of the Earth to the surface of the Earth by convection. And this is the same process that happens in a hot cup of tea or when you're boiling your spaghetti water on the stove. Hotter rocks tend to be less dense. Colder rocks tend to be more dense. Less dense things tend to rise. More dense things tend to fall. And so you set up circulation where hot stuff deep in the Earth tends to rise up towards the surface, cools off, and then sinks back again, setting up circulation cells. Okay, and it turns out that plate tectonics, we as beings living at the surface of the Earth, are essentially floating around on these convection currents. And things like earthquakes and volcanoes are actually manifestations of this circulation. Okay, so are there any questions about basic structure so far? I should say this is actually a computer model. It's a movie. There are many of these kinds of movies. This one is borrowed from Mike Gurnis at Caltech, showing how the Earth's mantle might start circulating. In this case, you can see it starts without anything happening at all, and then you see cold stuff starting to drip down from the surface and hot stuff starting to rise up from the core. Okay, so let's try to draw a connection between that and this, the shape of the surface of the Earth. And this is a map that is color-coded according to elevation. Okay, so these purplish colors are the deepest parts of the ocean, down below, let's say, 6 kilometers, getting down as deep as 11 kilometers in some places. Then the lighter blues are shallower, very shallow. Then the greenish colors are above sea level, but still fairly low in elevation, below 1,000 meters or so. And then in a few places in the Earth, of course, like Tibet or the Rocky Mountains, you get these brownish and eventually back to purplish colors where they're very high elevations again. Okay? And there are some systematics here, hopefully, that you can see. What's the most common color on this map? Yeah, these kind of deep blue colors are really common, right? They're most of the oceans. Okay, what's the next most common color? Yeah, green, I would agree with you. Okay, there are lots of areas of continent that are just a little bit above sea level. Okay? And I would also say that this very light blue color, okay, is also very common, even though it stands out very strongly. That's very shallow ocean water. Okay, so the most common elevations on the surface of the Earth, just from inspecting this map, would be fairly deep ocean of order 4, 5, 6 kilometers deep, okay, and fairly low-lying land, or very shallow ocean, between, let's say, minus 200 meters and 1 kilometer above sea level. Okay. And in fact, what we can do is we can go through this map and we can sample various points and make a graph. How common is this particular elevation on the surface of the Earth? What fraction of the Earth's surface has a particular elevation? And if we make that kind of graph, it looks like this. Okay, this is a histogram, for those of you who are familiar with that, where the x-axis in this case is just how common is that elevation. The y-axis is elevation. Okay, and you can see that there are two peaks, right? There are two fairly prominent peaks. Okay, it's not like the Earth's elevation is some messy munge with all kinds of random stuff in it. There seems to be a very strong tendency for elevations just barely above sea level or just a little bit below sea level, And a lot of the area of the Earth seems to have water depths of order 3 to 6 kilometers below sea level. There's a bimodal distribution. Lots of the Earth's surface is right near sea level, and lots of the Earth's surface is a few kilometers below sea level. And in fact, most of the Earth's surface is a few kilometers below sea level. That's the bigger peak there, the bigger area. Okay, so here's the basic question. We're living on a continent. We're living on actually one of the common colors. We're roughly 100 meters or so above sea level here, so we're actually kind of right on this peak. Okay, we're in one of the most common elevations you can find on the Earth's surface. Okay, why, sitting here in North America, a continent, are we right near sea level? Likewise, why is so much of the ocean a few kilometers below sea level? Let's see if we can come up with some explanation for that feature of the Earth's surface. Okay. And here's the basic answer. That this goes back to the rocks I was showing you before. In particular, it goes back to this difference between the oceanic crust being made of middling dense basaltic rock and being fairly thin, and continental crust being made of less dense rock and generally being quite thick. Okay? That difference, thicker, less dense versus thinner and slightly more dense, turns out to be, we think, the underlying reason why so much of the continents are right near sea level and so much of the oceans are a few kilometers below sea level. Okay, so I've already gone through this a little bit, but just to remind you again, and so you have a nice picture in your notes. Granite, density 2.7 to 2.8 times the density of water, typically fairly light colored. This is because it doesn't have very much magnesium or iron in it. Magnesium and iron tend to make rocks more dense when they occur. And this kind of rock is really common in California, actually. If you go to the Sierra Nevada, it's the most common kind of rock, broadly speaking, there. Or if you go down towards San Diego, actually, in the peninsular ranges, this is a very common type of rock. And even in the San Gabriel Mountains, it's pretty common around LA. Okay. An oceanic crust is basaltic, a little bit more dense, has a dark color, partly because it's volcanic and really fine-grained things tend to be dark, but also because it has a little bit more iron and magnesium in it, say 7 or 8%, maybe even 10% instead of 1 or 2%. And that tends to make rocks more dense. So this rock is maybe 7 or 8% denser than typical granites. That is, of course, if it doesn't have holes in it, those of you who are up close can actually see that there are little vesicles in this because it erupted at the surface and it foamed up with gas. This degassing process I talked about on Monday, actually, of course, if you include the holes, that makes it less dense. But for rocks that erupt underneath the ocean, generally they don't have nearly as much vesicle in them, so they end up being fairly dense. Okay, so continental crust, 30 to 40 kilometers thick, quite a bit thicker than oceanic crust on average. There are exceptions, but on average, a good number to remember for the thickness of continental crust is 35 kilometers. Oceanic crust, thinner and made out of basalt, something like 5 or 10 kilometers thick. Okay? It can be thicker in some places. If you go to like Iceland, for instance, which is a particularly thick region of oceanic crust, maybe 20 or 30 kilometers thick, that's kind of about as thick as it gets, and there are places where the crust is much thinner than that also, but good ballpark number, 5 to 10. Either of those numbers is good to remember. And of course, in both places, regardless of what kind of crust there is, once you go down beneath that, into the lithosphere and eventually into the asthenosphere, then you're in much denser rocks, more than 3 times as dense as water. Okay, another 10% or so denser than the crustal rocks. And once you get below 100 kilometers into the asthenosphere, that rock can flow. Okay, so if you push down on one part of the Earth, okay, below about 100 kilometers, if you keep pushing down for millions of years, the rock's going to start to flow out of the way. Okay, it's going to make a path, and the land is actually going to start sinking underneath you as you push it down. And in fact, we know this happens when there was a big glacial maximum, lots of glaciers near the Earth's poles about 20,000 years ago. There were big ice caps in North America. There are big ice caps over Northern Europe. There are big ice caps a few other places. And they melted. Okay, they're not really so big anymore. And what we observe, if we go to those places today, is that the land is slowly rising. Okay, there was a big load of ice pushing things down before. It melted away. Now the land is slowly rising back because the mantle underneath is flowing in, okay, because it's not under that load anymore. Okay, so the basic important thing to remember here is the crust, the lithosphere, are floating on a part of the mantle that can actually flow around in response to changes in pressure. And this means that the asthenosphere actually is a buoyant medium. Okay? Things can float in it because it can flow around them. Okay? And this means that we need to understand why some things float higher than others. And of course, eventually we're going to want to understand why some things sink. Okay? And it's basically coming down to Archimedes' principle, the same thing that causes boats to float in the ocean. Okay? The basic idea here is that if you have some solid and it's immersed or resting on a liquid, it's going to sink into that liquid or fluid, in the case of the Earth's mantle, which is solid but can still flow, until it displaces enough material to match the mass of the thing that you've pushed down into it. Okay? And so a good example of this would be a cargo ship. Okay? And of course, LA, we have a big container cargo port. We have ships that come in full of goods. They unload those goods. Eventually they get transported to trains and they go off to stores and stuff like that. And then the boat sails back, usually with much less load on board. Okay? And when it has that load on board, it has that extra mass of all those containers it's carrying, and that pushes it farther down into the water. Okay? So it floats lower than the boat that doesn't have a load. Okay? So any object in a fluid, including a boat and including the Earth's lithosphere, with respect to the asthenosphere, is basically resting on that fluid and being pushed up because the fluid is saying, hey, you know, I want my space. I want to flow into that space you're taking up in me, and so I'm going to push you out of the way. But of course, gravity is also pushing that object down. When those two forces balance, then you're at equilibrium. Buoyancy equals gravity, and the object is at rest. Okay. So how does this work intuitively? Well, if I have some block floating in a fluid, okay, what's going to tend to make this block float high? What property of the block is going to control how high it floats? I heard it a little bit. If it's more dense, what's going to happen? It's going to sink if it's more dense than the fluid. If it's the same density as the fluid or just a little bit less, how high will it float? It'll be right near the surface, but it will barely break the surface, right? And if it's like styrofoam on water, okay, much less dense, how's it going to float? It's going to sit way up high, right? Okay. So the idea is that we can apply the same logic to the Earth. Okay, so here we try to do a demonstration. Fortunately, the instructor spotlight is out, but I hope you'll be able to see this. Okay, so we have here a tank of water, which hopefully I won't drop off the edge, and some wooden blocks. And the wood blocks are two thicknesses. We have thin 2x4 blocks and thick 4x4 blocks. And we have two different kinds of wood. We have this lighter colored wood, and we have this darker colored wood. And these two blocks are actually the same kind of wood, just thinner. Okay, so again, I'm going to have faith that all human beings can determine density fairly well. So what I would like you to do is weigh these and determine which one is more dense. Just in your hand. Just hold up the one you think is least dense. So that's the least dense one, the darker one. And which one is more dense? Hold it up. Okay, so the lighter colored one is more dense. Do you want to try it and see if you agree or disagree? So hold it up. That's the more dense one, the light colored one, and the less dense one is the darker one. So you agree. Okay. So based on that, which of these would you expect would be more like continental crust in terms of relative density? Okay, continental crust is the least dense kind of crust, right? So it's like the dark block. Which of these is like oceanic crust? This one, right? The more dense type of wood is more like oceanic crust, which is more dense. Okay. So if I float these in water, which one would you expect to float higher? More dense or less dense? Plenty of time. There we go. Okay, so the more dense rock, or in this case the more dense wood, floats lower, less dense rock floats higher. Still on average it's higher even when they try to tilt over like that. Okay, so what happens if I take the same density, the same type of wood, but have a thicker block instead of a thinner block, or vice versa? So here let's look at these are the two light-colored pieces of wood. Okay, so the denser types of wood. Which one do you think is going to float higher? Okay, so thicker piece of wood. The bottom of the piece of wood is lower in the water, right? But the top of it is higher. Thinner piece of wood, top of it's barely breaking the surface of the water. Okay, so less dense floats higher, thicker, the top surface is going to be higher. Of course, we're all less dense than rocks. The ocean is less dense than rocks, so we're most interested in what's happening at the top. Okay? So we already established that oceanic crust in terms of its density was most like this light-colored block in the sense of being more dense than continental crust. In terms of thickness, okay, which of these blocks is most like continental crust? Raise your hand. Okay, is it this one? Is this most like continental crust? This one? Raise your hand. This one? This one? Not voting? Abstain? Okay, less dense, more thick. Right? So this is like continental crust. 35 kilometers thick to scale and less dense than oceanic crust. Okay, which one is most like oceanic crust? This one? Who votes for this one? All right, we got many more hands. That's right. Okay, so oceanic crust is thinner and made out of more dense material. Continental crust is thicker and made out of less dense material. And so if we presume that they're floating in the Earth's mantle, and if I can get this one to behave itself, there we go. We have thick, less dense continental crust standing high. We have thin oceanic crust lying low. Okay? And of course, the conceit here is that they aren't really floating in water because they're much more dense than water. They sink in water. But instead, they're floating on the fluid part of the Earth's mantle, the asthenosphere. It's solid, but it's plastic because it's so hot. It can flow, just like the water here is flowing around the blocks. And so the solid part of the Earth, the lithosphere, is floating on that layer effectively. And less dense, thicker parts, like the parts that have continental crust in them, are going to tend to float high. And thinner, more dense parts, like the oceanic crust, are going to tend to float low. Okay? And so if we have an Earth, a planet, that has two kinds of crust in lithosphere, continental crust and oceanic crust, which one's going to have the ocean over it? Oceanic crust. Not so hard, right? Because the top surface of that oceanic crust and lithosphere is going to be lower in elevation. If you dump water on it, it's going to accumulate here. Okay? And the continents are going to tend to stand high and dry. Now, it turns out, kind of interesting, right, that in reality the continent surface is right near sea level, and the oceanic crust, on average, is a few kilometers below sea level. It's an interesting thing to think about. I'm not going to go into it in great detail, but you may want to think to yourselves, why does that happen? Why does it turn out that sea level is really common for the elevation of continental crust? All right. So if we think of the Earth's lithosphere as being like wooden blocks floating on a fluid asthenosphere, okay, we would think that the continental crust is a really thick block made out of relatively not very dense material. And we could think that the oceanic crust is relatively dense and also fairly thin. So oceanic crust is low, continental crust is high. Okay, so coming back to this picture, now maybe it makes a little more sense to you. Thick continental crust floating on the Earth's asthenosphere, the surface is going to tend to be up high. Thin oceanic crust, thin dense oceanic crust, is going to not float as high on the Earth's asthenosphere. And so water tending to accumulate in the lowest elevations is going to accumulate in the ocean, okay, to an average depth of a few kilometers. So some statistics for you. As we've already mentioned, the average depth of the oceans overall, regardless of what kind of crust is underneath them, what kind of lithosphere is underneath them, on average something like 3.8 kilometers deep. Continents, the average elevation is actually pretty close to sea level, maybe a few hundred meters above. In terms of surface area, the Earth really is the blue planet, okay, a little bit more than 2/3 covered by ocean, a little less than 1/3 covered by land. In terms of the distribution of oceanic and continental crust, though, it's a little bit more even. Okay? Something like 59% oceanic crust and lithosphere, something like 41% continental crust and lithosphere. If we go back to the elevation maps, you can see that there are large areas off the coast of Florida, for instance, the North Sea in Europe, for instance, that are continental. Okay, they grade evenly into the continents, but they're still slightly below sea level. Okay, so there is a significant area of the ocean that's actually underlain by continental crust. That tends to be a very shallow part of the ocean. Okay, and these things, okay, in particular the average elevation, stems from the difference in crustal thickness, oceanic crust being thin and continental crust being thick, and the difference in density. Oceanic crust being denser and therefore floating lower, continental crust being less dense and therefore floating higher. Okay, just bear in mind that we're talking about the lithosphere of the Earth floating on a fluid part of the solid mantle. Okay. So for the last 15 minutes or so of lecture, let's look into a little bit more detail about what the shape of the ocean is like. We've hopefully given you some idea of this basic dichotomy we see between the dominant ocean depth of a few kilometers, these dark blue colors and light purple colors, and the dominant elevation of the continents right near sea level. Okay, but of course there's a lot more going on in this map than just that. Okay, you can see that some parts of the ocean are pretty featureless, generally fairly deep. Some parts of the ocean, like this funny ridge, are at somewhat lesser depths, okay, closer to the surface. They tend to form these ridges that circle the globe. What's up with that? And of course, as residents of Los Angeles, we're particularly interested in the interface between the continents and the oceans, the margin between continent and ocean, or between land and water. Okay, we're going to particularly look at that in some detail. And we're going to come back to that over and over again, because that turns out to be sort of the most interesting part. And then one final thing to talk about, there are some areas of the planet's surface and under the oceans in particular where you have these arcuate shapes that you may or may not be able to see from the back of the room that are particularly deep. So there's a little arc of purple colors here, very deep ocean water, and there are a few others around. There's a little arc here. There's actually an arc here which doesn't show up very well here. The deep sea trenches, the deepest parts of the ocean, turn out to have some interest as well. Okay, so let's start simple. The most common depth of the oceans, 3 to 6 kilometers deep. There are large swaths of the ocean floor that have roughly this depth that are not exactly featureless, but not the most exciting places topographically either. Okay? And we call those abyssal plains. Abyssal meaning deep, plain meaning flat. And that's pretty much their two defining characteristics of the deep, flat parts of the ocean. Okay, so over large distances, they have slopes that are far too small to ride your bike down. Okay, you could roll a bowling ball if the bowling ball didn't get slowed down by the drag of the water, and it would just keep going. And the basic structure of these relatively featureless, flat, deep areas of the ocean is that there's a layer of sediments in them. Okay, so if you were to drill down from the surface, you would first encounter muds, limestones perhaps, and then eventually you would reach oceanic crust at some depth. Okay, and then you would have the normal oceanic crust basaltic rocks underneath that. And these can be really big. Okay, this is a picture showing the east coast of the United States. So here's Florida, here's Cuba, Washington, D.C. would be up here, Boston would be here. And over here, this is Africa. Okay, and here's Portugal and Spain. Okay, so we're just looking at a picture of the North Atlantic Ocean here. And there's this big area on the east side of the Atlantic Ocean, which is an abyssal plain. There's this big area on the west side of the Atlantic Ocean, which is an abyssal plain. Probably most of the area of the Atlantic Ocean you would consider one of those two. Okay. But they aren't completely featureless. There is stuff going on there. And in particular, this isn't just for the North Atlantic, but there's a particularly good example here. You can see this chain of bumps, right? And depending on the size of the bump, we give it one of two names. If it's a relatively small bump, rises less than 1,000 meters from the ocean floor on which it sits, it's called an abyssal hill, okay, a deep hill. If it's more than 1,000 meters but hasn't quite broken the surface to become an island, we call it a seamount. Okay? And many of these little bumps are actually more than 1,000 meters tall, so that's called the seamount chain. And of course, you can see it forms a kind of linear pattern pointing towards Woods Hole. And so it's called the New England seamount chain. And here we have Bermuda, which is a seamount that got so big that it's actually poking up above the sea surface. There's an island there, Bermuda. One thing we'll come back to, particularly is a coda when we talk about plate tectonics, is why it's very common to see these kind of chain patterns. There turns out to be a reason why. And there's also, because of that pattern, earth scientists are very interested in understanding the relative ages and directions in which those seamount chains go. Okay, so let's focus in particular on margins, on the areas where you go from continent to shallow continental sea to deep oceanic lithosphere-covered sea, or underlying sea. Okay, and these are margins, continental margins. And we're actually going to make a division right off the bat, because it turns out there are a few different types of margins, but two that are particularly important that look relatively different, actually very different from each other. There are Atlantic style or passive margins, which are common around the Atlantic Ocean and the Indian Ocean, but they don't occur everywhere. It's just that's the typical place to find them. Okay? And these are typically broad and flat. I just showed you a picture of a good example, and I'll show you some more pictures. Florida and Virginia, the east coast of the United States, is by and large a passive margin. And then there are Pacific style or active margins, which are common around the Pacific Ocean, but occur in some other places like the Caribbean Sea. And these tend to be much narrower. You go from continent, land, to deep ocean much quicker than you do on passive margins. Okay? And they are typically adjacent to a deep sea trench, in fact. So the deepest parts of the ocean often occur fairly close to the continent near these active margins. And some examples are Chile, or in general the entire coastline off the Andes in South America, Japan, actually kind of pick your spot in the Pacific, California being a little bit of an exception. Okay, so let's focus in on passive margins first. These are the type you would typically find along the Atlantic Ocean. And if we were to take a cross-section, by the way, this is not to scale. In particular, the ocean is not this thick relative to the ocean. The ocean water depth is not this thick compared to the oceanic crust thickness. They're actually comparable. Oceanic crust is usually a little thicker than the ocean on top of it. But it's a good schematic. And a passive margin basically consists of a flat part of the land that grades into a relatively flat part of submerged land, okay, shallow ocean. Then there's a transition gradually tapering to deep ocean. Okay? And this flat area and the taper, by and large, consist of a big pile of sediments that have washed off the continents. Okay? You can think of continents, they're standing above sea level, rain falls on them, forms rivers, breaks down rocks, it carries them as far as the river goes. When the river hits the ocean, it more or less stops. Its ability to carry large grains of sediment diminishes, the grains fall out, and you essentially build up a pile of sediment where rivers meet the ocean. Okay? And over tens or hundreds of millions of years, that pile can get really, really thick. And eventually you make a broad, flat shelf. Okay? And you can see this pretty dramatically if you look more closely at a map of the ocean depths and the elevation of the land. This is a picture, again, of the southeast coast of the United States. So here's Florida, Miami's down here, up through Georgia, South Carolina, North Carolina. And here we have this broad, flat area of continental shelf. It's underwater, but not by much, 100 meters maybe. Okay. Low slopes, typically less than half a degree, typically underlain by a big pile of sediments. Underneath that sediments, there may be continental crust, there may be oceanic crust, there may be something that's kind of a hybrid of those two things. And it extends out from the shore typically tens or even hundreds of kilometers. It's a pretty broad feature. Okay, so if you were sailing out from Savannah, Georgia on a fishing boat and you were fishing for something that lives a kilometer down, you would have to be on the boat for a while traveling out before you finally reached water that was that deep. Eventually, however, there is a break in slope. And in fact, in some places, including off the coast of Florida, there may be more than one break of slope. There's a break of slope here, and there's another break of slope here. But for the sake of simplicity, let's just assume that there's only one, like there is up here off the coast of North Carolina. Okay. And that contrasts to the continental shelf in being generally a much steeper slope. Okay. Very flat, and then all of a sudden it kind of goes down. And these features, because they're so steep, they tend not to be very wide, tens of kilometers wide. And eventually, you get so deep, you're basically at the depth of oceanic crust without very much sediment on it, and it tapers out and becomes flat again. And eventually, of course, you're going to reach the abyssal plain, but in between, there's a transition called the continental rise, continental shelf, there's shelf break, continental slope, and then it becomes tapering less and less steep. Eventually you get to the abyssal plain. In between we have continental rise. It's relatively flat ocean floor, but it's not as deep as the ocean floor would be if there wasn't this relatively less dense, thick pile of sediment sitting on it. Okay, you can think of this as being a sedimentary fan. You can think of it as being an apron. It's a gradual transition from the continent to the deep ocean. Now, in this picture, it's kind of too coarse to see very many details. There are lots of interesting things going on. There's like a really steep slope here. You get into the Bahamas, you get these flat spots of the seafloor and very low-lying land. Okay? But nonetheless, if you look closer, you can actually see even more detailed features that tell you something about how this structure comes to be. Okay? And one of the best examples of this is just up the coast here near Monterey Bay. So the town of Monterey Aquarium, if you ever get a chance to go there, it's great. It's down here. Santa Cruz is up here. If you keep going up this way another 50 miles or so, you get to San Francisco. Okay. And it turns out that Monterey Bay has a very prominent bathymetric feature in it. It has this meandering canyon going out to the deep ocean. So how do canyons get formed on continents? What created the Grand Canyon? Yeah, the Colorado River carves the Grand Canyon, right? In general, when you have rivers flowing across the land, they can erode it away if they're traveling fast enough, okay, and make a canyon. Is there a river here? No, not really. And it's so deep, okay, it gets more than a kilometer deep. Sea level goes up and down over geological time somewhat, okay, but this is so deep. There's no way it was ever above sea level. Okay? There didn't used to be a river here that just got drowned. So the interesting question is, how did this thing get there? Okay, what could carve a canyon when you're already underwater? Well, it turns out that there's a type of current that can travel with enough velocity, enough scouring power, that it can actually carve out a canyon even though it's already underwater. And this is another example of density layering. Okay, more dense things tend to go towards the bottom. Okay? And in this case, what's happening is it's all underwater. So the fluid in this case is still water. How do we make one piece of water more dense than another piece of water? Okay, temperature change will do it. If you have really cold water, it might be more dense than warm water. Is there something else you can do to the water? Okay, salinity, that's good. So if you have really salty water, it's going to tend to be more dense than fresh water. Is there anything else you could do? What if you mix some mud into it? Mud is like continental crust, so its density is maybe 3 times that of water. If you have little grains of mud suspended in water, you make the water overall more dense. So if you have a suspension of lots of mud in water, that parcel of water is going to become more dense, and it's going to want to flow downhill. So what we are seeing in this movie is a picture of what's called the density flow. In this case, a debris flow. If it had less sediment in it, we could call it a turbidity current, where water and mud are mixing together and making a fluid that together is more dense than pure water and therefore tends to flow out along the bottom, sometimes at very high velocity, potentially for very long distances. Okay, and in this case, it's depositing, but you could imagine if it was going fast enough down a steep enough slope, it would actually be able to scour out a canyon. All right. So when we come back on Friday, we'll talk a little bit more about features of the ocean floor, including deep sea trenches and mid-ocean ridges, and we'll start talking about plate tectonics.